Well, again, folks, in 114, today we're going to be covering section 12.2. Let's just look at the calendar real quick to verify. Okay, today is Wednesday, April 7th. So we're going to be covering 12.2 as per the schedule. The packet that I have for you today is hefty. There is quite a few pages in it because there's a lot of different types of diagrams we have to discuss. I have Old Faithful, my template here for some vocabulary. And then I made this diagram to summarize the different types of diagrams and tables that you will see in this section. I'm going to discuss this as we go through it, but try to print this page. You could always add more information to it as we discuss. There are 3 examples that I want to do with you. I swiped these from an older book I used to have, but I like them very much, and it is very good at illustrating each of these. Then there are tables to sort of help you work through the process. And there's this first one. Then there's the procedures. I stole this from your textbook because it is very concise. All right, especially up here. All right, and there's a formula down at the bottom. There are separate files, but I sort of blended them together into this packet. Here is another blank one of these because you have to do it twice. The procedures, again, the second page is now, there are 2 formulas that you would really want to pay attention to towards the bottom here, and a description of each of these. Then there's a table I made for basically creating a histogram. A description of stem and leaf. A blank for that purpose, doing example 3. And then there's a discussion of pie charts. Right, and here's the actual example in the book. There is some useful information down here where it says solution. But I wanted to show you an example, how to do it brute force, because I think you'll learn a lot in the process if you have this exercise. Right. And I'm going to make available an Excel spreadsheet that you could keep if you want, or manipulate, just to show you what it's all capable of. Okay, in terms of making charts. Okay. Having said that, let me get busy over here. Here we go. Okay. All right. Remember, section 12.1 was about collecting data, and 12.2 is now actually generating a diagram, a picture, basically. Okay. But there's a lot of vocabulary to get out of the way first, so let me do that. Command, turn on. Alright, adjust the lights here. And turn on the projector here. Which I never remember to plug in. Okay. That's pretty good. Okay. Let's start with the terminology. I don't know if it makes sense to close this door, but let me see. Let's make it easier. Right. Okay. All right. Now, the first thing that the phrase you're going to hear thrown around a lot is the term frequency. Okay. And just like its regular usage, it basically just means how often something occurs. Okay. But then this will be tied to the word distribution. We'll see or hear about a frequency distribution. And fair warning, this is basically a T-shaped diagram, a chart, at least in the context of this particular textbook and the MyLab assignments. It's a table listing some things observed, and their corresponding frequency. Red marker is on its way out. A table listing some things observed. I'm saying some things because it's more than one thing. And the corresponding frequency of those things. Right. What does it literally look like? It's a T-shaped diagram. So a simple table like this. You have frequency on one side, and you have the item in question on the left side. So you'll see something that looks like this. Okay. My diagrams that you see that I offer as a handout have a third column, only because when you have to do this brute force, it helps to keep a tally so that you don't lose count. But what you eventually translate it into is an Arabic numeral. Push this aside, just keep it out of trouble. So you'll see a Hindu Arabic numeral here. As the frequency. All right. And there's this phrase. Right. And I hope that this green cooperates, because it's always debatable. Class. And some people call it a bin. Is that visible? Looks like it's okay. Put this aside just a little bit. A class or a bin, that's why I'm using a forward slash here. And it's width. Right. This is a number used to indicate how wide each section of a frequency distribution should be. So, it's literally a number. Crappy markers. Used to indicate. I write in capital letters, I've noticed sometimes, just intuitively, because it is a little bit easier to see. It's not me yelling, I swear. Right. Let's see if that's visible. Looks like it's okay. A number used to indicate how wide each section of a frequency, I'm going to have to abbreviate here, distribution. You'll see what I mean when we get there. There's a formula basically attached to this. It's a little questionable. Basically it involves subtraction. You just have to subtract two things. There's a formula written down, but I might as well take advantage of this space, and hopefully it's legible. You would have, in theory, a second class lower limit, I'm just going to abbreviate it as LL, minus the first class lower limit. This is, in fact, available on the actual handout here, so let me just point to it in case it's not visible. At the very bottom of the descriptions here, I'm referring to this. I typed this in two different chunks here of different color. the second class lower limit minus the first class lower limit. This is known as the class width. It's basically how wide the class or the bin would be. Okay. Now, having said that, you will. This may come up. I'm doubtful, but I'll mention it anyway. You might hear this phrase, modal class. This is essentially the class, or bin, whatever you want to call it, with the greatest frequency. It has the most data. You've probably heard of mode from types of averages: mean, median, mode, and mid-range. Right? The mode has to do with the number that occurs the most often. Well, if you have a modal class to extrapolate, it's the greatest frequency. Right. Now, in contrast with class bin and width, there is another formula, which is called class mark. I'm going to reiterate this probably later in the conversation, but this is, instead of subtracting, as you would in this case, to establish the class width, right, class mark is the midpoint of each class, which means it will be a different number. And it's this formula, right? You're going to basically add two things and then divide by 2. So what are you going to add exactly? The lower limit of a class plus the upper limit of a class, and then you're going to average them basically, so you'll divide by 2. In this case, it's the numbers involved in the same class. In the case of class width, you're using numbers from 2 different classes. All right. Again, just to make sure that this is legible, all right, in the handout there's a formula for that as well, and I put them, I had the good sense when I made this to show you the distinction here. Here's again class width, second class lower limit minus first class lower limit. Right, these are from numbers basically taken from 2 different classes, and the class mark is just the lower limit of one and the upper limit of the same. Right, in this case, you're adding and dividing by 2 because you're more or less taking an average. All right. The difference between these as well is that this is the same number no matter which classes you're talking about or involving in the calculation. This is going to be a different number every time because it's a point, literally. So it moves, right? You could use one to calculate the other if necessary. You'll see later. Right? Beware, this will be different for each class. That midpoint should be a different number. Right? Whereas this will be the same number no matter what. Stop that. Yeah, okay. One more thing I'm going to fit in here just because I need to, and then we'll get into the diagrams, is the histogram. So just because I've run out of space, I'm going to basically put it here. This is being temperamental today. A histogram is basically a bar chart without gaps. Okay. That's the most literal description of it. It's a bar chart, so you'll see rectangles, right? But there'll be no space in between the rectangles. What is it for? It's a graph meant to illustrate frequency distribution. Key here is the following. Right? I need space, so I'm going to write it up here. There's a horizontal scale and a vertical scale. The horizontal scale are the ranges of the observed classes. They're columns, really. Right. The vertical scale is the actual frequency. All right. There'll be different heights. Okay. One interesting thing, these do not have to be calibrated the same. The calibration of the horizontal scale could be a different calibration, different increments when compared to the vertical scale. Okay, that's enough of terminology. Now let me discuss this. The actual diagram that I have prepared for you that summarizes a lot. Okay. Blues have been annoying today. Keep this right handy. This is an overview of the different types of diagrams that you're inclined to see in this section. Let me describe it from top to bottom. So that is basically the train of thought. And let me make that larger just for that reason. Okay. Now this is, you will see often a rectangle, right, with some data thrown into it, right? There's a technical name for that. It's called a data array, all right? It's basically just a container with the actual numbers involved in it. In this case, it has letters, right? It's organized to the extent of it being in a rectangular sort of regimentation, all right? What you do with that is that you translate it into one of the basic statistics tables or diagrams, right? And you may be able to do more than one if you wanted to, but these are your choices. All right. So on the far left here, you have the category known as frequency distribution tables. Right? Again, frequency distribution tables are basically just T-shaped diagrams, in which case the frequency is the whatever numbers that you see on the right side of the T. All right. But there's two separate subcategories here. There's categorical frequency, and then there's grouped, or what you might call continuous frequency. These are regular ordinary bar graphs, if you're going to go the whole 9 yards. Right? You could translate these T-shaped diagrams into bar graphs, in which case they'll be gapped. Right? So you'll see bars, but there'll be an obvious gap in between them because they're discrete items that you're talking about. That's why they call it categorical. All right? A type of bar chart that is slightly more complicated would be for the grouped frequency distributions. Right? Still originates from a T-shaped diagram, right? But they're a continuum. Right? One category essentially is immediately connected to the next. Right? One flows into the next. It's a spectrum, if you will. All right? A sort of blip, you know, a sudden wave, right, of information. Right? Anyhow, I get a mess here. These are the type that you would turn into, potentially, if you're going to go the whole 9 yards in this train of thought, into the bar chart that is known as a histogram, right? And in that instance, it just means that there's no space between the bars. So you'll see something like that. Okay? So make that distinction. It's very easy, right? When you think categorical, gapped, true bar chart, grouped frequency distribution may originate from this table again, but you could translate it into a histogram. Right? If you keep following this train of thought, the next thing that you could do, you could translate a histogram into something known as a frequency polygon. Right? A frequency polygon basically looks like a mountain range. In profile. And it's basically superimposed on top of the histogram. So you'll see something that looks like this, a zigzagging sort of mountain that connects all of the tops of the bars. The midpoints is what those actually will be, which is the reason why we've discussed them. Each one of these is midpoint. All right, the class mark. Each one of these middles of each of these bars at the top. You superimpose this sort of line graph on top of the histogram, and it makes something that, again, it looks like a mountain range, right, in profile, right? It would be called a frequency polygon because it is a multi-sided sort of shape, all right? If you were going to go even further still and dumb down the picture so that there is no bars behind it, and it's debatable, I suppose, but you just, rather than start from 0 or go to 0, you might just see the interesting portion of the graph. All right, that is actual tops, all right, is the bottom of the graph, all right, and that would be a zigzagging line, all right, it's really just the top of the mountain now. All right, that is a line graph. Okay. All right. Stem and leaf diagrams are another alternative, right? All right. The advantage to having a stem and leaf diagram is that it basically looks like a histogram on its side, which is why I say it's sort of a sideways histogram, but nobody actually draws the bars around it. What it does is it allows you to still see the actual numbers involved. That's what I mean when I say this is illustrating frequency while preserving a view of the data. The actual numbers are still visible. All right? And it's on its side. So if you can imagine a histogram sideways like this, it might look something like that. The thing is, nobody ever bothers to draw the bars there, right? It's just how long the data sets are. Okay. And then you have pie charts, which if I had to say that I had a favorite, this is my personal favorite. All right? Pie charts are for comparing parts to a whole. Right? Comparing parts to a whole. All right? The wedges of the pie are a percentage. The whole would be 100%. I feel that this is really the most intuitive, and it's a nice way to represent information to people. Very often in a magazine or in a newspaper, what do you see? You see a circle graph, otherwise known as a pie chart, all right? Because it's easy for people to understand, all right? It can be a little misleading if you're not careful, all right? When you see the number 100, 100, it's really a percentage. So it's not really telling you how many people are involved in whatever survey have you. People see 100 and they go, oh, 100 people. Not necessarily, it's proportionate. Anyhow, that's an overview of the different types of tables and diagrams that we're going to see. All right, and I'm going to give you an example for virtually all of these. So with that in mind, let me start with this. In my packet, all right, after this page, there is the 3 questions that I stole from an older resource. So I'd like to do these with you because I think that will get your feet properly wet. All right, we're going to start with this one. It would be technically example 1. I just didn't label it as such. Look for the array with the A, B, C, D in it. E. And I'll erase this. Okay. I'm going to try to keep these 2 things side by side. I just need to see the data array more than anything. And then maybe adjacent to it, I'll pull up my first table here. Okay. I need these 2 things in tandem. All right, so what you're seeing on the projection is basically this first example, all right, with the A, B, C, D, E, D, E, rather, array, all right? And this is meant to illustrate a categorical frequency distribution. So if we were going to make a diagram after the frequency distribution, because this table that you would see here and here, that is the category in tandem with the frequency here, would be the actual frequency distribution. This is as you would see it in my lab. I put this 3rd column in here in the middle because if you had to do this brute force, all right, it would be helpful to be able to just keep a tally, all right? It's a simple way to, keep track of your data, all right? Translating from the array into categories and relative frequencies here. Okay? Now, why are they categorical and not a continuum of one frequency into another? Because we're talking about vitamins here, all right? A health food store recorded the type of vitamin pills that 35 customers purchased. I'm reading it backwards, unfortunately. All right, during a 1-day sale, construct a categorical frequency distribution for the data. All right. Now, what you have to do initially is look at the array, right, and just kind of get a feel for what distinct categories do you see here? In other words, which distinct letters in this case, and the letters represent types of vitamins, what type of vitamins are in this exclusively? Right? There's nothing about B12 or anything like that, right? It's just A, B, C, D, E, right? So what you would do if you have a nice blank worksheet like this, and I'm providing that to you, right, is basically take a ruler, right, and maybe draw some lines as we go through this across the page. I didn't do that because, you never know how many categories you have. But I would use capital A, capital B, C, D, E, and then put lines across to keep it nice and organized. So what you'll see is this. All right, there are A vitamins. There are B vitamins. There are C vitamins, D vitamins, and E in this array. All right. Now it may seem a little weird, all right, but the activity of translating this into a frequency distribution is the tedium of going, how many A's are there, right? So you could count them, but what I would do is this, all right, to make it easier on you as you go along, as you progress, start with the first letter. The first category is A, all right, and read it left to right, row by row, all right? So here you go, you have A, one tally mark. And in the case of the second row here, you have another tally here. And the third one, you have a third, coincidentally. And then in the fourth one, you have two, so one, and then you cross it for 5, right? That's how you make tallies. If you've ever watched old cartoons, right, you see some cartoon character, whiling away the hours in jail, that's what they always do. They fill up the cell with, tally marks, right? All right, so that's 1, 2, 3, 4, 5. 1, 2, 3, 4. To make it easy to count, you cross 5. All right, and then the last row here, you just have an extra one. Okay. So that's a good way to keep tally, especially if you have something more complicated than just letters. So trying to establish a technique, if you will. All right. How many do you have total? All right. That is the actual frequency relative to type A here. So write that in the standard Hindu Arabic numeral 6. Okay. Not too complicated, right? And now again, maybe to spare yourself the trouble, cross out all the A's. Right? It'll make it easier as you progress. Right? Next one, B would be a logical letter, right? So in the first row, you don't see anything. In the second row, you see 1B, right? And then in the third row, nothing. And then in the fourth row, you see 2, 1, 2, all right? And then in the fifth row, you see another 2, so 1, 2. All right, and what you translate that to, of course, is an Arabic numeral 5. 5. Okay, now cross out the B's. B. B, 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 B. Okay, and continue. The C's, it looks like that's probably the most. In the first column, you see 1, 2, 3. The first row, you see 3. In the second, you see 1, right? In the third, you see 1, 2, 3, 4. So 1, 2, 3, 4. In the fourth, you see 1, 2. 1, 2. And in the fifth row, you see just 1 extra. So they have it. I think I'm miscounted somewhere. Let me just verify. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There should be an extra one here. Sorry. So now I'm going to say, okay, that's 12. And then to make it easier as I do the next category, I'm going to cross out all the C's here. Right, from the array. All right, D's, 1, 2, 3, and that looks like it's it. All right. So that's a 3, 1, 2, 3, and then the remainder are the E's. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. You really don't have to do the tally at that point because it's the leftover, but just to be a good sport, I did it. Right. I prefer to complete the thought rather than just leave it hanging, right? All right. And that's it. All right. As I said, when you're creating a frequency distribution, it's just a T-shaped table. All right. And on one side, the far right, it should be frequency as an Arabic numeral, Hindu Arabic numeral, and on the right side would be the category or the group. All right. The third column in the middle again is just to help you. All right. You don't have to do that, and you won't see that in your MyLab assignments. They'll just have it compacted together, 2 columns. All right. All right. Let's do a grouped frequency problem now. Now, just before I get into it, let me show you again. This is a procedure about how to craft a grouped frequency distribution here. I would read this, all right? It's useful to you. I'll just point out some points here. All right, the classes should be the same width, right? That is, the breadth of the groups should all be the same amount, class width. All right, the classes should not overlap. One is butted up against another. And each piece of data should belong to only one class. Now, what I would highlight is this sentence here, all right, where you see 5 and 12. All right, so maybe I'll do myself a favor and I'll project it. All right, I don't want to really throw this away, so I'm going to just put this aside for a moment and then just highlight some information for you. Okay. What is most important from this, I feel, and that's why I swiped it. Okay. There has to be consistency, right? The classes should be the same width. They're consistently the same. All right, the classes should not overlap. That means that one immediately attached to another. One is immediately butted up against the next. Right? Each piece of data should belong to only one class. Now, what's really, I think, really super imperative that you know, all right? In addition, it is often suggested that a frequency distribution should be constructed with 5 to 12 classes, all right? If there are too few or too many, the distribution may become difficult to interpret. For example, if you use fewer than 5, you risk losing too much information. If you use more than 12, you may gain more detail, but you risk losing clarity. Let the spread of the data be a guide in deciding the number of classes to use. All right. What this is alluding to here is essentially decide what the minimum is, decide what the maximum is, you know, from looking at the array, and then try to fit it into, start with 5 maybe, or 6, right, the lower numbers, and break up the data, the mass of data, into groups of, you know, so many that there are 6 distinct classes, you know, 5 or 6, something like that, all right? And you can really only decide that based upon what the minimum is and what the maximum is, right? You do, to make it easier on you too, you want the division to be easy, so you want it to divide nicely. All right. Anyhow, bear that in mind. 5 to 12 classes. That's basically the spectrum you're working in. All right. Now, to illustrate how to do this, let's take a look at the example again that I swiped from elsewhere. And I'm going to scoot this up here. Right. It's this array that you see here. This is going to be a little bit of a nuisance because I have too much stuff overlapping, but let me read it to you first. In one math class, the data below represents the number of hours each student spends on homework in an average week. Construct a grouped frequency distribution for the data using, they're telling you in this class, specifically 6 classes. Alright, why? Because it will make the math, how you chop things up a little bit easier. The division would be basically without a remainder. Alright, anyhow, that fits into our spectrum of 5 minimum and 12 maximum. Okay, anyhow, if you analyze this array, alright, let's try to figure out what the minimum is. Alright, the minimum number of hours studied is, it looks like it's 1. Alright, what is the maximum? Alright, the maximum is 18. Alright, now if you were to subtract these, you would get 17, which is not a number that divides very easily. But being that this 1 is as close as it is to 0, let's just say that we're going to divide 18 by 6. Alright, so we'll figure out what the each class width will be. Alright, this is a little bit more brute force than just using a formula, but in this case you really need to. Alright, I need a little bit of space to write, so I'm going to take this down. And try to scoot this over to make it fit. Come on. It's not cooperating. There it is. Okay. That's probably the limit at which I can make it fit. No, I don't want to do that. Oh, you suck. Okay. That's a little bit better. Okay. Alright. Just to narrow our focus here, here's the array that we would be zeroing in on. Right, this is the vitamin problem, and this is a problem for stem leaf plots. Anyhow, we are advised to divide into 6 classes. So what you would need to do in this case is get a ruler, take another one of these blank diagrams if you have to make one from scratch, and chop it up into 6, rows, like this. Hopefully I planned this better. No, that's too much. What I really should do is get out my ruler and measure how long it is from here to here and divide nicely, but that's a bit cumbersome, so I'm not going to. One, two, three, four, five, six. That's good enough. Okay. Now, instead of writing A, B, C, D, E here for the categories, these are groups. All right, and the groups are often presented as hyphenated and encapsulated in the parentheses from one number to another number, a lower boundary to an upper boundary. For each class. Okay, so basically this is what we're doing. All right. Now, let's figure out how wide the distance between the lower boundary and the upper boundary will be for each of these, because remember that has to be consistent, right? If the maximum is basically 18, right, and we're not starting too far away from 0 to begin with, really the lowest number here is 1, all right? Now let's just say that it's 18 divided by 6, right? And that will be how much? What's 18 divided by 6, right? 3 numbers wide is the class width. Right. Now I know that you might be going, hey buddy, didn't you give us a formula for this? Yes, and as a matter of fact, it's at the bottom of the paper, right? But this is something that you would use when the diagram is already established. We haven't been given a histogram yet, right? All right, or a frequency distribution. We're setting it up, all right? So each one of these has to be 3 numbers wide, the class width, right? So if you look at this array here, the lowest number is 1, and if it's 3 numbers wide, it would be 1, 2, 3. So it will stretch basically from 1 to 3. And then the next class will also be consistently 3 numbers wide, starting with the number immediately after 3, which is naturally what? 4, so it'll be 4, 5, 6. I'm just putting a hyphen in between to show you that this is a group, a stretch. And then it would be 7 to 9, right? And then 10 to 12, and then 13 to 15. And then because it works out nicely, 16 to 18. That's the ideal, okay? Sometimes you have to go back and fix it, like you had some inkling to begin with, and it ends up not being the best, so you just start from scratch. Don't ever feel bad about perfecting it after the fact, because you're feeling around in the dark to begin with, right? Anyhow, these are the grouped frequency distribution, right? Data that exists in this group, data that exists in this group, right? That is including the endpoints here, the boundaries. What again you have to do is, by brute force, read this left to right, right? Keep a tally just so you don't lose your space, right? And then maybe make it easier on yourself by crossing stuff off that are that group. So here you have 1, 2, 3 things that would fit into this first category here. First group would be better to say. Second row, 1, 2. Third one, third row, just 1. And fourth row, 1, 2. And the fifth row, 1, 2, it looks like. Yeah. So you should have 10. Alright, so I'm going to translate into the Hindu Arabic numeral 10, and then cross everything out that's from that category to make it a little bit easier as I progress. You can see that this is a bit tedious, but this is how you would do it. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Maybe just for distinction, I'll use a different color now when I do the next one. Things that fit into the group of 4 to 6. Right. 1, 2, 3. 1, 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. One. One, 2. Okay, so 5, 10, and another 4, 14 in this case. Reluctantly, we'll use green again. Things that fit into the spectrum of 7 to 9. 1, 2, 3, 4, 2, 3, and 4. I made one dodo error before. I did count it, but I neglected to erase this, yeah. Alright. I'm going to count the blues now just to verify, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, yes. Okay. Picking up where I left off here, that's another good reason I use a different color, it makes it easier to keep track, right? This is this one here. Next one. Looks like 1, 2, 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And this is another 10. Now what fits into 13 to 15? All right. Oh, pardon me, 10 to 12. 1. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And that's it. 6. That looks like total here. 6. Now I'm out of colors, so I'm going to go back to red here. What fits into 13 and 15? 1. 1, 2, 3. 1, 2, 3. 1. So that's a 5 again. And then the last ones, I'll just circle here to make it a little bit easier on myself. 18, 16 to 18 category. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, there's our frequency distribution. These are the groups, all right, which again, we really decided from the minimum and maximum and that they'd set the standard at 6 classes, all right. 18 divided by 6 divides rather nicely, right? The actual frequency distribution you would see would be just, again, these 2 columns, all right? The tally is there if you had to do this brute force. Right? I don't think that in MyLab, if I remember correctly, that they make you do that too much, right? They more make you use the formulas to figure out how consistently wide this ought to be, right? Now, just to prove that this formula is correct, right, what you'd be given is a table like this to begin with, and you would see these groups isolated as such. Usually there's a little hyphen and they're in a little pocket in a parentheses. All right, the class width should consistently be the same number. All right, if you were to calculate it, would be the second class lower limit minus the first class lower limit. So you start with the one that is a little after. This is the second class lower limit. This is the first class lower limit. What's 4 minus 1? A distance of 3, right? If you did the next one, this is the second class lower limit, and now this is the first. What's 7 minus 4? 4 minus 1 is 3, 7 minus 4 is also 3. And then 10 to 7 is 3. And then 13 to 10 is 3. And 16 to 13 is 3. You see that it is consistently the same class width. Shouldn't put this here, but that's what I mean. Class width. Okay? 3, 3, 3, 3, 3, all the way consistently from top to bottom. Okay? All right. That's just to verify. All right, now take a look at this next. We're going to make an actual histogram from this. So let me get rid of this now, and I'll move this out of the way as well. And go back to procedures just to highlight certain information that would be good to have, right, from this same handout. Right, this is the procedures for constructing a histogram. Highlight some information here. Histograms and frequency polygons are statistical graphs used to illustrate frequency distribution. Yes, we know. All right, a histogram is a graph with observed values on a horizontal scale. All right, as I was mentioning before. All right, here's a glorified bar chart, otherwise known as a histogram. The scale that is the horizontal scale, all right, are the observed values. And the frequency is the vertical scale. The horizontal scale and the vertical scale, as I mentioned before, the calibrations do not have to be the same. Right? There is one other caveat here I should mention. This is worth saving. Right? The horizontal scale need not start at 0. That's horizontal. All right. The vertical does. All right. All right. Vertical scale must start at 0, but the horizontal doesn't. The calibrations of this can be different increments this way and different increments this way. That's perfectly allowed. Okay. It may be necessary to break a vertical scale that was done in display of the stock B on figure such and such page. What that is referring to is like sometimes on a standardized test you may see a graph that looks like this and they put a break in it like this. All right, it's just to indicate that there's a gap in the scale that is irrelevant. All right, so where you're looking is maybe just above or just below that. Okay. All right. Now, let me show you how we would translate basically what we just compiled here, right, into a frequency distribution, right? Brute force, all right, because brute force is what's going to make you learn it. All right, and to that end, I have this diagram for you. It's a blank. I may have to minimize just a wee bit. There you go. Okay. All right, it's kind of fun actually. All right, remember what we were just reading, right? The observed, I hate to say the word category because I don't want to conflate it with the alternative, all right? But it may be more intuitive to call it that, rather than groups, right? These columns are going to be the spectrum of each one of your groups, right? So we had established, and I'm not going to start over 0. I'm going to leave a little space here intentionally and leave a little space after the fact. I prepped this exactly for this particular problem. What I'm going to do is I'm going to put these little parentheses groups down here that we had established, right? Leave this column empty, leave this last column empty. So this is the 1 to 3 group. This is the 4 to 6 group, 7 to 9, the 10 to 12, the 13 to 15, and the 16 to 18. Okay? And even though it might be a little silly, the increments that I'm going to put here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right? The height of this frequency distribution need not be taller than the maximum, in the data array. so since the maximum number of hours that a student studied according to that survey was 18, again, I purposely prepped this so that it would fit, all right, for this particular problem. Now, here's the fun part, all right? You take the Hindu Arabic numerals that are the frequencies, and or you could take the tallies and theories as well, and translate them into a block. Right? So what I'm going to do is, because green is so faint to begin with, I'm going to go to the spectrum group category here of 1 to 3, and in each one of these little blocks, the cells here, looks like I might have drawn this in Excel, all right, make a little X or a dot or a mark of some sort. I think X's are easy, so I'm going to put an X that will be 1 increment tall up to the point of the frequency. And it's a little hard because I'm casting a shadow, but I'm going to go so far as 10. All right, this is the 10th block, so this is how many X's tall this would be. Right? The next one is 14, right? So maybe I'll start at 14 and work my way down here. Okay. And then the next one is coincidentally 10. So I go to my 10th block here. Okay. And then it is 6. And then it's 5 and 5. Okay. All right, now the next thing is, this is basically a bar chart at this point, right? Because you see these columns that are basically establishing the histogram. But we don't want gaps, which is why the grid lines here are going to be handy. What we'll do now is we will put a cap, at the maximum here of 10, and at 14, and at this 10, and at this 6, and at these 2 5s. And then make it, for the fun of it, sort of follow the guide of the column line here down to 0 frequency. Right? And you'll see that they're not categorical, they're grouped frequencies, in fact, because they're butted up against one another. The continuum stretches from 1 through 18, just establishing this boundary as, switching from 3 to 4, 6 to 7, and so forth. Okay? All right, and there you have it. Now, if you want to, you can scribble this in a particular color. I sort of do opposing line barriers like this so that they look distinct columns. If I don't have different shades to work with, I would probably do this with different markers if I had better markers. All right, but you see that there are 6 classes, grouped classes, right? And that's how they would look in the style of a histogram. Right? The visual aid that transforms a frequency distribution into a type of bar chart known as a histogram. All right? Now you might wonder, well, why did you leave a gap here and leave a gap here? Right? The reason is because if you are then asked to instead go a little bit further here, we start again with a frequency distribution, and we've translated it into a histogram. If you want to make this a frequency polygon, there's a little bit more work to do, right? It isn't too difficult. You can get away with doing it without really much of a calculation, right? Because you're just going to put a dot here, 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 and here, and there, all right? But let me just remind you of the formulas that we have established, right? On this piece of paper, description of the process, right? We have those two formulas, right? The class width. We already know that it's going to be 3 wide consistently across each bar, all right? But then there's the class mark, all right? Now, why do we care about this? The class mark is the midpoint of each of the bars. This is a different histogram, but it's just remarkably similar to the one I just did, all right? Let me pull that up for a moment. I don't really want to move this. So I'm going to just minimize and put this here for a moment. On the same page here, all right, there's a description here of the frequency polygon. Just to emphasize some points in this paragraph, let me highlight it for you. The frequency polygons are line graphs with the scales that are the same as the histogram, which means if you have a histogram, you could superimpose a frequency mountain range on top of it. To construct a frequency polygon, you would place a dot at the corresponding frequency above each of the observed values. That means you would put a dot at the top of each of these bars. Right? Then connect the dots. When constructing a frequency polygon, always put 2 additional classes. That's this one over here and this one over here that is not part of the data array. All right, one at the lower end and one at the upper end on the horizontal scale. Values for these would be, these added class marks are not needed on the frequency polygon. Since the frequency of these added classes is 0, and the endpoints on the frequency polygon will always be on the horizontal scale. Okay, so we're going to put dots basically on this, and what this is explaining is that where should you actually put the dots? You should put place the dots according to the class mark, right, which is calculated from the first class lower limit plus the first class upper limit divided by 2, an average. This is a number that is going to change, in theory, over and over again. So let me put back my histogram diagram here, which thankfully I've preserved it. Right. If you have a bar chart already, you can kind of get away with not worrying about this, but let me show you the calculation involved here. On this side, I'm going to do what they're really asking, which is to calculate the class mark, right? Which is, again, the midpoints. And just for the sake of contrast, over here, I'm just going to show you, again, the class width, because they're suspiciously similar, but they're not the same. The width of each. Okay. The formula for calculating class mark, right, is the lower limit of a class plus the upper limit of the same class divided by 2. It's going to change because it's a midpoint, all right, per class, right? The formula for class width is still this. It's the second class lower limit minus the first class lower limit. And this will not change, it's going to be consistently the width. All right, so if you did the calculation for the first one, right, the lower limit of this class is 1. The upper limit for this class is 3. which makes this 4 divided by 2, which is just the midpoint is 2, right? So where's the midpoint on the horizontal scale? It would be just about in between, you know, this line and this line. That would be 2, right? That's the class mark. Midpoint, right? So on the frequency end of this, you would put a dot at the very tippy top here. So just to emphasize it, I'm going to make this a red dot here. All right. The truth is, looks like a cherry on a cake, right? The truth of the matter is, because you have a diagram like this, and you could probably visualize what the center would be, all right? You could very easily just go ahead and do this right now. Put cherries on all of these cakes. Okay? And we're just going to connect the dots. But sometimes they ask you to specify what the actual number was. Here, 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 and here. And it might not be easy if you don't really know the graph too well. So realize that you have this formula to fall back on. All right? Now, you could do the same calculation again and again and again and again and again. But what you might do instead is maybe spare yourself a little bit of trouble, right? Rather than going, well, what's the class limit here? And then you go, all right, it's going to be 4 plus 6 divided by 2, and then you would figure out that that is 10 divided by 2, and this would be 5. What you have as an alternative is to incorporate this information that you would know, the class width, because the space from here to from this midpoint to this midpoint is going to be consistently the same. It just happens to be the same thing as the bar's width to begin with. It's just scooted over to the midpoint. So if you already know that the second class lower limit is 4, and this is 1, and the difference is merely 3 wide, then what you would do is, just to get the calculation, right, you take your midpoint, otherwise known as class mark, and you add the class width. And that will give you more midpoints. All right. So if the first one we assume is 2, and you add 3, then the next one would be 5. All right. If that is 5 and you add 3, the next one would be 8. If it's 8 plus 3, the next one would be 11. Right? If it's 11 plus 3, the midpoint would be 14. If it's 14 plus 3, the midpoint would be 17. Right? These things that I've circled are the class marks. The class mark here, 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 and here. The class width is naturally consistently the same number 3 for this problem. And then this is just what the result would be that I've reincorporated. All right? 8, 11, so forth. Okay? So 17, this last one as well. All right? Now if you wanted to, right, you could figure out where the exact point would be here, but it is kind of pointless, right? Waka waka, right? So what you would do, boo, is spare yourself the trouble. You purposely left the gap here, put a dot just about the middle there, and just about the middle there in the back. All right? And now finally you could draw the mountain range. So I'll do that now. All right. The mountain range is, you should really take a ruler. So in setting a good example, I'm going to use my particulars t-square here and try to carefully draw straight lines. Connecting each one of these midpoints. If it gets you to remember, I will do anything absurd. This is the way of the teacher. This is the way. All right? Be a clown a little bit. All right? At least a little. You don't want to lose, people's respect, I suppose. But you have to be willing to make yourself look like a fool, if only for the reason that you teach the moral lesson. That none of us, we're all fools here. All right? We're all feeling around in the dark. We're all learning. So take comfort, you're in good company. Students, teachers alike. A teacher is just a person who is a student for the rest of their life. It's a curse. I'm sorry, I make a big deal out of nothing. But anyhow, you see, right, the frequency polygon superimposed upon the histogram. Right, and if you want to, you could erase the, the histogram at this point just to emphasize the mountain range. And then color it in if you really want to. I'll sacrifice this marker. Okay. Something like that. If, again, you wanted to go the whole 9 yards and do a line graph, right? A line graph, I want to say, is, I don't think it goes down to 0 necessarily. It usually looks something like this. I don't think it's mandatory one way or the other. So you would see something like that would be just the tops, okay? Where the data starts, where the data ends, right? If you wanted to, you can connect it down to 0 again, but I don't think that's mandatory. Right. The points are really what's relevant. Okay, so 3 types of graphs, all contrived from, the same data, right? A grouped frequency distribution, a T-shaped diagram. All right. Now, let's discuss the stem and leaf. Let me get rid of that. Nope, wrong way. Okay, let me just emphasize some information from here. And then I'll do my 3rd example with you. I'm doing pretty good on time. A stem and leaf display is a tool that organizes and groups data while allowing you to see the actual values. That's really the distinction here, right? And that make up the data. To construct a stem and leaf, each value is represented by 2 different groups of digits. It's going to be a T-shaped diagram again, right? The stem part is on the left side and the leaf part, quote unquote, is on the right side, okay? Now it's usually 2 digits, 2 or 1 digits here, and the unit 1 digit, which is usually the ones place, or what this book calls the unit position, all right, as a leaf, right? So for example, if you had a number like, let's see, the number 6, all right, you would break it up into a 0 and a 6, even if that sounds silly, right? These are basically, the stems are like your categories, right? Okay, that's okay. All right, now let me give you an example that I have prepared for you. That is in the original packet. This 3rd problem that you see here down at the bottom. All right, this is an example for stem and leaf. Here's the array. It's smaller than the other arrays, so thankfully less complicated. All right, but let me try to get it on the same screen adjacent. And I'll pull up a different T-shaped diagram here. All right, I need this, which I'm going to back off just a little bit and put that there. and resurrect this thing. Okay. All right. This is from a book from about a decade ago.
What a good message as far as racism and
Let me see. If I can get this to cooperate. Humor me, I'm sorry. All right. Alright, let me start with this, I'll read it to you. Alright, it's no secret that gas prices have fluctuated wildly in the last few years, but between the years 1980 and 1999, they were surprisingly stable. According to the Energy Information Administration, which is like a made-up government agency, the data below represents the average price in cents, right? That's hundredths of a dollar, right? Per gallon of regular unleaded gasoline in the United States, right? Draw a stem and leaf plot using this data array, right? So when you see something like off to the very far upper left there, 119, all right, just realize what that means. It means, 119 cents, which is $1.19, right? All right, that looks like it's fine. Now what you need to do as you're going through this is just eyeball the array. Again, try to figure out what's the minimum. Right, what's the maximum? It'll help you be a little bit more strategic. Right? If you read this from left to right, it might be a little hard to read because it's small, but can you see that in the projection? There's a bit of a glare. Hopefully that's a little bit better. Let me see if I can turn that up a little bit. It's still kind of faint. All right. I'm going to scoot this over here. Maybe this will be a little bit easier to read. All right. $1.19, $1.31, and so forth. What appears to be the smallest number in this array? It looks like it's 86. All right. What is the largest number in this array? It looks like it's 131. All right. So they didn't tell you that you have to, sort of break this up into different categories. All right. But when you are constructing a stem and leaf diagram, all right, you really are doing exactly that. All right. You're going to break this up into categories as well. Right? And you'll determine that how many of these horizontal lines you would have, right, based upon this minimum and maximum. There appears to be things that are in the 80s. So I'm just going to put it over here, 80s, 90s, that's 90 cents, 100s, things that are in the 110s, that's where that's an S. Some stuff that is in the 120s, and then maybe one thing in the 130s. So the way that this particular problem works out is that you have 1, 2, 3, 4, 5, about 6 categories, if you will. Right. I'm putting a little foot cloud around this because this is how I'm trying to break up it into stem and leaf. So if you have something that is in the 80s, right, the unit that is the ones place of 80 or the like would be here, right? Truth be told, right, if you had to do this nice and neat, right, I really should have done this myself. They don't give you graph paper, but I would construct this on graph paper if I was setting a better example. The reason for that is that the graph paper has little boxes all over it, right? So it will give you a consistently wide space here, right? You'll see as I go about the process. I'm going to do the first one. The only number that is in the 80s group, right? Group category here. Whatever you want to call it, right? Is 86. Right? I'm going to do employ a similar technique to before. All right, I'm going to go, all right, what's in the 80s? That thing. But rather than make a tally mark, I'm going to put an 8 here, and I'm going to put a 6 here, because it appears that there is nothing else that is in this category. So I'm going to cross that out now. All right. Now, what I need to do, since I didn't put this on graph paper, and I want to try to keep it as neat as possible, is I'm going to draw vertical lines now. And graph paper would keep this consistently the same column width, right? I'm going to go ahead and use my actual tool here itself to establish what the column width would be here, right? So we got 1, 2, 3, humor me, 4, 5, and you can continue on and on and on. 1, 2, 3, 4, 5. I'm going to be a good guy, and this one time I'm going to draw another 5. Again, graph paper would have been more strategic of me, and I apologize. This is why people buy ledger books, right? If you go into accounting, at least old school accounting. Six, 7, 8, 9, 10. I think that's fine. Red, I think. Let's see what I can get away with here. Started to be a little off filter. That's okay. Alright. So you have the basic T shape in purple, and then you have my fake grid lines that I have constructed here. Alright, now we can continue. Right. The only thing that is in the 80s is this one example. Let's see what is in the 90s. You don't have to be strategically putting things in numerical order, but I would put forth the effort, right? It would maybe make things a little bit more obvious about what the mode would be if you wanted to figure out the mode. So, right, you don't have to, you're not obligated to arrange in numerical order, but I would, anyhow. All right. So let us see. All right. Scan across for things that are in that 90s category. You have 90 and you have 90. So of the 90s category, you're going to have a 0, and then you're going to have another 0. It's nice that you start with that. Scan the next line. Do you have anything else that comes after 0? 90? No. All right. The second, now you get into this third category, the hundreds. This is where you're going to have, instead of a single digit number in the stem, you're going to have 2 digits. All right, because again, we're trying to make the leaf basically the ones place. So one more time, I'm going to make another column here, just to set a good example. Like so. Break the radiator. Okay. Now, this will be things that are in the hundreds. So 1, 0. The 110s would be 1, 1. The 120s would be 1, 2. The 130s would be 1, 3. Right? So 100s, 110s, 120s, 130s. That is the teens, basically, right? Okay. We used 86, 90, and 90. All right. Now we'll do of the hundreds category. Again, try, if you can help it, to put things in numerical order. Again, you're not obligated, but it would help you in the long run. So we have 100. Let's check if there is anything else that is 100 here. No. All right. Let us see what comes after 100. It would be 101 through 109. All right. So if you scan this, and thankfully it's not too much stuff, the next thing would be 106. So you would have 106 over here. Right. This is 2 digits and then 1, 2 digits and then 1. That's 100. That's 106 respectively. Right. So we use this much. Right. Anything else in the zeros here? Doesn't look like, right? When you get to the 110s, there's quite a lot of stuff, right? So let's see if there is in fact a 0 first. Right. 110, 110, 110. No. But what you see immediately is a lot of 111s, right? So you have, overall, you have 2 111s. So it will be 1, 1 for that one and for that one respectively. And then the next number after 11, it would be 12 naturally. So let's see how many 12s there are. There's, looks like one example of a 112. Right? So I'm going to put 2 here. All right. And that would be it for the 12s. Now let's see what comes after that. 113. Let's see if there are any 113s. There's one. Anything else? There's a second one. All right. So there's 2 113s. I'm going to put a 3 here and a 3 here. And keep crossing them out. It will help you keep track. All right. And eliminate the possibilities as you proceed. All right. After 113 would be 114. Is there anything else that is 114? Doesn't look like. So you're going to cross out 114 here. And then actually 115. There's an example there and there. So there'll be a 5 and a 5. Cross out, cross out. All right. And any 116s? There aren't. There is a 117, so I'm going to put a 7 here. And there is one example of a 119, so I'm going to put a 9 here. All right. Now, what you're going to start noticing, again, is that there's a certain height, if you will, sort of a sideways height. Jesus. Why'd you do that? All right, if I were to stretch this down to the purple line here and sort of look at it sideways and then put a cap around these, what does it kind of look like? You don't have to ever do this, nobody ever does it, all right? It kind of looks like a histogram, all right? What it is illustrating is that this particular category, this group, if you will, the 110s in the thought balloon, is the category with the most data. Right? So far, I should really be a good guy and continue when we continue them. All right. Of the 120s, is there anything with a 0 to start with? No. Anything with a 121? No. There is a 122, so I would put a 2 here. And then there are 3 123s. All right. So I would put a 3, and a 3. Cross those out. That seems to be the apex here. And then the last one, the only thing in the 130s category is in fact 131. So that's it. All right. Again, it's more or less a sideways histogram. All right. It allows you to see the actual data though. All right. Remember when I drew a histogram, I just used X's to indicate, and then eventually bars, and then eventually, the mountain range to indicate the height of things, right? But in this case, we'll use, as long as you do it again on graph paper, where there is a consistent increment in terms of how wide these individual data points would be. They should be consistently the same width in the columns here. you will see that this is, in fact, again, where most data resides, right? Right, now, just to remind you from our terminology, that phrase from before, modal class, that is the class that has the most data. In this instance, it would be the 110s is the modal class. As you can see, it's the longest, all right? It's the histogram that would, in theory, be tallest if it was turned 90 degrees, okay? Then there's the actual mode, which, again, you're not responsible for, but we are going to cover mode in section 12.3. Mode is the data point that occurs the most often. So if, again, you strategically put things in numerical order, it would make it a little bit easier to judge what the mode is right now, because it would be the same digit recurring the most often, right? You have 1, 1 here, you got 3, 3, that would be bimodal if that was the case. But when you get down to the 120s, the actual mode is this, it's 123. That's the mode, right? 123. Okay? The modal class is the one with the most data, but the actual mode is here in the 120s. Okay? Moving on. Alright, now one more thing, the pie charts, and we'll do an example together. Alright, let me just emphasize some information from the handout about pie charts, because there is something in here that is very useful. I gotta erase this. Let's see. Circle graphs, also known as pie charts, are often used to compare parts to a whole. Right? That's really the most important thing. It's comparing parts to the whole, right? And the whole is always, no matter how much data is involved, in the style of a percentage, a whole would be 100%. Okay, that means that any of the pie wedges would be some smaller percentage than 100. The real important thing from this, I feel, this is an example about Ringling Brothers, all right, is down here, right? In my lab, if memory serves me, they ask you a question like this, right? They say, well, there's 800 people that were surveyed, but based upon percentage, all right, how many in each individual category? Right, to determine the number of respondents in each category, right, what would you do? You take the percentages and you multiply times the total overall. Right? So if in this particular problem that is alluding to circuses, it would be 800. So what are the people favor the watching tigers apparently? All right, it would be 38% times 800. Remember, when you have a percentage, you would have to convert it to either a fraction or a decimal. So in the style of a decimal, it would be 0.38, and therefore 0.38 times 800 would give you how many actual people out of the whole, rather than just explaining an amount of people as a percentage. Okay, so that's important from this, right? If you had to actually figure out how many people per category, it's a percentage times the whole, the total overall. Okay? Now what I want to show you is something that I had done with a class from a couple of semesters ago, and I still like it. If we were together, if it weren't for Corona and we were together, I would walk you through this exercise, all right? Because I think it ties up a lot of loose ends all at the same time. So it's an opportunity as a teacher, all right, to fix what's broken, all right? Let me show you something. This is a diagram which I want you to keep for the rest of your life if you find it useful. Right. I took a survey of to illustrate how to construct a pie chart brute force. Right. How to construct a pie chart, shall we say, brute force. Right. Brute force is the most basic, intuitive, hands-on way to do something. When I'm using that phrase, right? I don't mean to denigrate it, right? You should always, I feel personally, to set a good example as a teacher, right? Start with brute force because it will give a person a feeling, right? Right? We're not robots, right? We need take for granted that numbers are non-emotional. Just read a temperature scale. Tell an American that it's 20 degrees outside, and they will go brr. Whereas the rest of the planet will hear the number 20 and go, oh, it's a nice day. There's one is a Fahrenheit, one is a Celsius scale. All right, that number 20. Anyhow, we have feelings about numbers intimately, right? Even though we may be oblivious. So how do you get a human, right, to really understand something, right? Start with the most basic interpretation, the brute force way of doing something, right? Then you could develop more skills after the fact, but it's never one thing in lieu of another. You want to cultivate as many skills as possible by the time you are an old person. Okay? Anyhow, so the example that I had was to take a survey of your favorite genre of movie. Right? And I can't do this because I have no audience really. But I decided to establish these categories. Right? And I'll show you how this basically will unfold. Right? I kind of grouped things in pairs because I needed to. Right? So A would be the category of action, adventure. Right? So think of like Die Hard or some movie with a lot of explosions. Things like that. Maybe Indiana Jones. Which is like some things are cross genre, granted, but just to kind of shift things to one category or another. For the next category B, I decided to group together sci-fi. I hope this is legible. There's a green. And fantasy. So think hobbits, or some kind of aliens of some sort. Robots. I like sci-fi is personally, and fantasy is my favorite sort of category. But not to corrupt you. But think of things that are like that. It's very fictional. It's not real. It is really plausible in real life. All right. Then the third category, I decided to group together what I would call horror and thrillers. Now, you might say, well, aren't those the same thing? Well, that they scare you, sure. All right. But here's my personal definition, and this is totally arbitrary, I realize. All right. A horror movie, in my mind, is not just scary, it is also potentially gory, so like a lot of blood and guts and stuff like that. And I explained that to my students too at the time. A thriller, on the other hand, is more not what you see that frightens you, but what you don't see, what your mind makes you worry about. This is more like Alfred Hitchcock kind of thing. It's psychological terror rather than a physical terror, Then the next category would be something like drama. And perhaps, just to give it another one, biographies, which I also like very much, biographical films. And then the last category, because I'm running out of markets here, comedy. And although it isn't really fair to group these things together, I will anyway. Cartoons, right? Animated films. Cartoons tend to be humorous no matter what, right? With rare exception, like maybe some horrifying incarnation of Pinocchio, which is a terrible cartoon. And I hate it. It's just evil. Also, The Last Unicorn, not funny. right? Watership Down, things like that are just really terrible. But generally, cartoons tend to be funny at some point, all right? I'm just kind of forcing two things together at once, not to have 10 categories, I have 5 here, okay? Granted, some things could be cross-genre. Something like an Indiana Jones movie would be potentially a science fiction adventure film, you know, but I'm going to compartmentalize. So with those conditions, I told my students, and this was in like spring of 2017, all right, let's take a vote, all right, you decide, don't vote more than once, which of these choices, based upon my explanation and interpretation of them, do you like, right? And I went around the room, there was like 20 people, including myself, right? And I took a tally, right? They raised their hands, and I would count people, right? And this is the way that it worked out at the time, all right? Tally of 3, all right? People liked action adventure the most, right? Science fiction, same, right? Or fantasy, 3 people like that at most. What, to my surprise, all right, and I'm not judging really, all right? What the demographic of Middlesex County student, all right, favored at the time was horror thriller, all right? So out of 20 people, this is how many people like this category, right? The overwhelming majority, as you will see in a moment, right? Dramas, just 2, all right? And comedies, just 4, right? So what you would do if, again, if the whole point of this is to construct a pie chart to reasonably explain, you know, what is the favored category, you know, give a person a feeling for what is the most desired genre of film, what's your favorite movie genre, right? This is the actual brute force thought process, right? You take the tally and first of all you translate it into a Hindu-Arabic numeral. So this is obviously 3, 3, this is 8, right? This is 2, and this is 4, right? If you count these, right, you will see down at the bottom here, though I didn't make the extra space, I should have, right, some totals, right? 3 and 3 is 6, 6 and 8 is 14, 14 plus 2 is 16, 16 plus 4 is 20 people was surveyed. You can tell that from counting up the tallies. They did not vote more than once when they were doing this, at least I made sure of that. All right, they had to stick with one category or nothing. All right. And if they didn't vote at all, then it would be less than 20. They wouldn't be counted. All right. You translate the Hindu-Arabic numeral into a fraction. Right. A ratio is a more generalized way of saying that. So it's technically it's the frequency of voting: 3 people, 8 people, 2 people, 4 people, over the sum of the frequencies, which in reality is the 20 people who voted. So how would you translate this into something that's a little bit more mathy, if you will, right? Well, this would be 3 out of 20, right? And this would also be 3 out of 20, right? Use that phrase, out of, because I think it's a little bit more intuitive, right? Such and such out of the total. Something out of something else, right? This is 8 out of 20. This is 2 out of 20. And this is 4 out of 20. Okay. Then what you need to do is to translate that into a decimal ultimately, because that will make converting into a percentage, which was what we're really after here, the percentages. All right, it'll make it a little bit easier. You can, in many instances, convert a fraction directly into a percentage, but sometimes it doesn't work out so nicely. So spare yourself the trouble. All right, divide the top number by the bottom number. All right, that's 3 divided by 20, and establish what the decimal will be. Thankfully, these are not going to be infinitely repeating, any of them, just because it worked out of 20. It happens to be a nice figure. So what you would see, 3 out of 20 is really 0.15. Right? 8 out of 20 is 0.4. Right? 2 out of 20 is really 1/10, so that's 0.10. And 4 out of 20 is 1/5, right? So that would be 0.2. Right? Now, I didn't do it, but I will show you something else also. this is a way, again, of tying up a lot of loose ends. I would teach a kid in junior high, middle school this stuff because, again, it will be more meaningful to them and they'll fix some issues that they may have in terms of arithmetic at the time, right? If you added fractions, right? 3/20ths, 3/20ths, 8/20ths, 2/20ths, 4/20ths. If you added them all up, how many 20ths are you going to get? 3 plus 3 is 6, 6 plus 8 is 14, 14 plus 2 is 16, 16 plus 4 is 20/20ths, right? That's not a coincidence. If you added up these decimals, what number should you get in theory? If you would verify, you would have to collimate this, add the hundredths place to the hundredths place, the tenths place to the tenths place. Ultimately, what you would get is this, 1.00. That's not a coincidence either, right? No matter how many people participated in this survey, that's what you would get as a decimal no matter what the problem is, all right? That would be equal to 1. 20 over 20 is 1, so it would be the total number of people over that same exact figure, right? So if you did 25 people, it would be 25 out of 25. If you did 100 people, it would be 100 out of 100, all right? It's a way of tying up loose ends because it will give somebody a project that will illustrate, you know, how these things are related. All right, next one. If you're going to convert a decimal to a percentage, it's super easy. It's just a decimal times 100. Remember the effect. When you multiply by 100, what happens to the decimal place? It moves twice to the right when you multiply. So if you could just envision this going scooting over like that, and then tacking on a percent symbol, there you have it. It's 15%. In theory, you could do the same thing with a fraction. You just have to be a little bit more careful. If you did brute force top times top, you'd get 300. If you did brute force bottom times bottom, that'd be 20. 300 divided by 20 is the same figure. A slightly more strategic way of doing that would be to cross simplify whatever you can. 20 divided by itself is 1. 100 divided by 20 is 5. 3 times 5 is 15. Right? Anyhow, in the decimal form, it's usually favored because it's a little bit straightforward. Right? So there you have it. Right? 40%, 10%, 20%. Now again, if this math is all correct, and it should be every single time, right? When you add up the percentages, what percent would you get as a maximum, that is a total down here, along with these other totals? You would get 100%. Every survey, every time, right? You're not going to make a mistake, right? It's a way of verifying and of tying up loose ends. All right, now the last thing is a little bit arbitrary. When you're drawing a pie chart by hand, right, you would need a protractor, right? And you would have to be able to measure out with a good deal of precision, all right, and accuracy, all right? How you would establish the number of degrees, though, it's either you take this original ratio of 320, and instead of multiplying by 100 as I did in this case, multiply by 360 instead. Or you could take the decimal equivalent of that fraction in blue and multiply by 360, and that will probably be what people are more inclined to do because they have a calculator. Anyhow, I don't fault anyone for that. The way that it works out is that 3/20ths or 0.15 or 15% of 360 is this. It's 54 degrees. And then at 54 degrees again, coincidentally, 0.4 or 8/20ths times 360 would be what? 144 degrees, the way it turns out, right? If 360 is the maximum, and this is a chunk of it, a portion of it, it would naturally be a smaller number, all right? Just to do it one time. If you had 3 over 20 times 360 over 1, again, pull the same trick. If you can, simplify. 20 divided by 20 is 1. 20 fits into 36 one time with 16 left over. 20 goes into 160 8 times. 3 times 18 is 24, carry 4 is 2 is 54, all right? There's more than one way to do it, as is often the case in math, and cultivating mental flexibility, a very good thing, all right? So 0.10 that times that is what, 36? And twice as much of that, 0.2 times 360 is 72 degrees. Now again, in keeping with verifying the totals here, all of these will add up to 20 out of 20. All these decimals, every single problem will add up to 1, the decimal point if you like. All of the percentages should add up to 100%. They do. If you added up all of the degrees, what should they be as a maximum? How many degrees in a circle? 360 you could verify. Right? Now the whole point of this exercise was really to establish these number of degrees, because that is how wide these are different wedges. I'm not going to make you do it, of course, but it would be a good mental exercise, right? If you made a kid, again, if you're going to try to incorporate a number of different subjects all at once, this is it, right? It's statistics, it's geometry, all right? It's basic arithmetic, it's fractions specifically, and decimals and percents, all right? And it's fun because it has to do with, something that people like, movies, all right? Anyhow, I was after these numbers, now I will show you, all right, what I'll do with them. Right. In the old days, what you would have done is, boy, this is really sad, but I have to do it. You would take a piece of blank paper, all right, and rip out your protractor, right, which measures degrees. And again, it's arbitrary because it's 360, right, and then measure 54 degrees, and then measure it again, starting from where you left off. And then again, 144, starting where you left off, 36 after that, and it should be 360 the whole way around. So I kind of need the space, right? And I'm going to minimize this, and I'll pull up bootleg paint here to hopefully illustrate, all right? I do not have a nice circle, all right? So I could take my lamp off. Let me see. I'll kind of wing it, all right? That's a circle, right? As long as you would use a compass, because a compass would, first of all, tell you where the center is. Looks like a Pokeball at this point, right? And establish a line where you start that 0 degrees, right? All right. Then you would take your protractor, and it doesn't matter what size the protractor is, and line it up with that line, that is the radius from the center to the edge of the circle that you draw, and then measure out 54 degrees along the edge. So this would be approximately there, right? This, unfortunately, acrylic makes it a little bit hard. And then you would take a ruler, all right, having established that dot, and you would draw to the edge of the circle at least, right? And this first wedge, that is from the 0 line, right, to where it would be 54 degrees on the edge here, right, is the action adventure collective, that is people who like this the most. Normally when you have a pie chart, you try to fancy it up a little bit. You give it a color, and you tell you'd say that it's 15% of people. That's more meaningful, all right? Never mind how many people were actually polled. And then you would shape it in like this, something like that, right? It's kind of fun, all right? I think it's fun, all right? When you are trying to establish the next wedge, right, it coincidentally happens to be the same dimension of 54 degrees, all right? You would, instead of starting at the 0 here, you would pretend that this is 0. So really, what does that mean? It means that you're going to take your protractor, and again, it doesn't matter how small it is, all right, and read out what would be approximately 54 degrees again here. I'm going to make a little dot, all right, and then with your ruler, connect the center with the edge again, all right? And then you have the next category, right? 15%. This is the Sci-Fi fantasy group. Alright, and again, normally what you do is you try to make it attractive, so you color it in somehow. Informative and attractive. Alright, and then you have that wedge. They should be the same size. Now when you do the next one, again, you start from where you left off. So, you continue along, and you would line that up at the center, and that's 0 now. And you would count out 154 degrees. 90 would be an L shape, and then 144 would be just shy of 145, so you'd have a dot roughly there. And then you take your ruler once again. And don't break the radiator in the process. And connect it like so to the edge of the circle, and you label it once again. Right? So this is clearly where most people favor a type of movie. Right? This was, although I'm not sticking with my original color scheme here, the horror thriller genre category here. Okay, and then again, we would try to fancy this up by making it colorful. If you didn't have a sucky marker, like I do, as I always seem to. They're rebelling now, they're mad at me. And I don't know if that's any better. Alright, and you do this 2 more times, just to be a good guy, I would do it. Alright, again, where you left off, you would measure out 36 degrees. So along this edge here, you would have a mark roughly there. Alright. You would do this with greater precision if you weren't like me and you're kind of like using, giant tools as if you were the smallest man on earth. As if I were, Stuart Little here, and I'm just gonna have everything a little bit too big to handle. There. And this last wedge here would be, well, this one here would be 10% of people who favor drama, right, or biographies. And then, in theory, if everything was measured accurately, right, and sometimes it's not because of the lack of experience with this tool here, the very last one should be 72 degrees. I'm going to just kind of verify as best I can. Let's see. It's a little off, but this is representative of what should be 72 degrees from here to here. Alright. And that would be 20% of people who like comedy and or cartoons. Alright. That is the brute force, old-fashioned way of making a pie chart by hand. And the reason why I still respect it is because it gives a person literally a relationship to what they're doing. They have literally a hands-on experience with this. It fixes a lot, it makes up for a lot of sins, all right? Often by the time a kid, bless you, a person reaches middle school, they've already been completely turned off to the subject of math, right? They had some bad experience, somebody yelled at them, all right? They got yelled at and, they're scared, all right? So they'll not be inclined to really want to participate. This is where statistics can, again, make up for a multitude of sins, right? Making a pie chart is equal parts statistics, all right? Geometry, all right? And basic arithmetic, all right? So converting fractions to decimals, decimals to percents, and so forth, all right? And all in one project, all right? Isn't that cool? I think it is, all right? So if you find that useful, all right, by all means, swipe it and incorporate it wherever you'd like to, all right? And make it personal. Now, just to show you, all right, nowadays, and I would bring this up after the fact, right? Nowadays, a person doesn't do this so much by hand, even though I would teach that. All right, what they would do is they would use an Excel spreadsheet or the equivalent of Google, or in theory, Apple even has its own software that simulates an Excel spreadsheet. I myself feel most comfortable with Excel. All right, and here's what you would do. There's another place where you could bring the subject, you know, to relevance. All right, in Excel, if you're not familiar, I'll try to blow this up a wee bit. You know, view. There's 200. In Excel, if you're not familiar, every one of these boxes is a glorified calculator. All right, if you wanted to use it for that purpose. It's different from a calculator in this regard. When you use a handheld calculator, what do you do intuitively? You type whatever it is that you're trying to calculate, and then you end it by pressing equals. And then it gives you the answer. You hit the equals button last. All right? If in theory you wanted to use Excel, because now you have the power of a full-blown computer, not just a handheld computer, you would do this exactly backwards. So if you wanted to, again, this is not really practical, but you would hit equals first, and then you would hit, 2 times 2 asterisk is a 2, and then you hit enter, and it calculates, it leaves the answer behind where you entered the sequence of numbers in operation, right? You hit equals first, right? That is something you could do if you wanted to. What is more practical in Excel is to not make it do simple calculations like that, right? It is to take advantage of its features. If you want it to do a calculation for you, you have to use equals. If you just more or less want it to be a label rather than a calculator, don't hit the symbol for equals. You could just literally type into the box, and it's not going to go into any sort of convulsions. It's not going to have an error message or anything like that, because, all right, it just understands that, all right, this is just a label. So what I did was I took, at some point in the conversation, I took my humble graph here, and I made it categories in the Excel spreadsheet. It's basically a replica of this, but it's using Excel spreadsheet. So categories here, I wrote what they were, all right. Tallies. The only thing is I couldn't actually symbolize tallies, so I left them as Hindu Arabic numerals. And then when I got down here to the totals, this is where I made it do a calculation. All right. Again, you're not responsible for this, but I want you to see that this exists as an idea. If you analyze this, all right, you could tell it. I'm going to just delete this for a moment. Right, you see that everything went into give me an error message basically here. It's because all of this information that followed was dependent upon this figure here. What you can do as a slightly more sophisticated calculator is basically cut and paste and highlight. Once you have the established data that you have physically typed, here, 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 and here, in place of my tally logs, you can hit equals, all right, and then highlight these. Right, and what you see shows up as basically coordinates that are something like, or akin to the board game Battleship. If you've ever played Battleship, you know that when you're trying to sink another person's ship, you would quote a letter and a number in sequence. This colon is more or less like a hyphen. So what you're telling the computer software to do is look at the data that is from this place to this place. It's in the style of a coordinate rather than its literal figure. All right. Now what I should do, I have to delete this, is tell it to do some specific operation. You could physically type plus, but the actual function is sum, and then it's in the style of a function, so they have it in parentheses like this, right? And then I'm going to close the parentheses, because if you don't, then you'll get a syntax error, and it goes into convulsions. And then hit enter. And then you can see that it fills in the rest of the table, because everything was dependent upon this number, right? Now again, more or less as a label, I wrote these in the style of a date because I wanted it to just be a label, all right? So that's why I didn't really, this is the one column that didn't get affected when I removed the 20 here, all right? The decimal number is, if you analyze these things from a calculation rather than having typed it, I'll put a little window here, and you see up here, all right, and this bar, it's a little faint, but you'll see it says equals C5, meaning that particular place, all right, and then divided by is the forward slash, and then I put basically the coordinates of the total, all right, which happens to be the number 20. Could I have typed the number 20 here? Yes, I could. Now, it's a little bit hard to see, but one thing that I put in here as well is I put dollar signs, all right? I'm going to write it over here just in case you're curious, all right? What you see over here, all right, that is exposing what is really underneath this answer, all right, is this sequence typed equals the location of the data according to battleship, right, C5, all right, divided by, and then I put the dollar sign, and then the location of the 20 here. So it would be C, dollar sign, and then 10. This is a little archaic, this sort of syntax that you have to abide by. The reason that you put these dollar signs here, rather than just simply the coordinate C10, is because you kind of, when you put these dollar signs, the dollar signs more or less freeze this particular block, this cell, as a reference. All right. If you didn't do that, what the software is sort of pre-programmed default to do is that when it does the next one, it would scoop down, all right? And then it would draw information from an empty block in this case. So if you put these dollar signs in there, it's saying, no, don't change that, just keep using this, all right? All right. Anyhow, I'll show you. Here, let me just delete this. All right, and I'll type it again, all right? If you put equals, and then you don't have to physically type C5, you could just go with your mouse over to here and go, all right, that one. I want to divide. The calculator just understands division as a forward slash, all right? And then go over to what the total is, because that's the denominator of this fraction, 20 here. But be careful, all right? It doesn't move, unfortunately. Put the cursor in here, and just put the dollar sign in front of the letter and then in front of the number, all right? And then you can see how I already have a graph drawn up underneath it. It's starting to try to draw a picture. Now, you might say, well, that's tedious, and why should I even bother with that crap? All right? The whole point of Excel is that once you have established what the calculations are involved here, what the formulas are, all right, the functions, you don't have to keep doing it over and over again. Imagine you had 100 data values and not just 5, all right? Once you have it established and it's all correct syntax, again, you're freezing this particular cell in place, all right? You could just grab this and then drag it down by the little box in the corner here, and it will automatically do all of the calculations for you. That's the benefit of it. So here, I'm going to show you. If I go over here with my mouse and I put the little cross here, holy, I guess, right? And drag it down, it automatically does the rest of the calculations, right? If I put the mouse on this and click on this to highlight it, you'd see that it's drawing information from the next logical cell in the sequence of this column and dividing by 20 because I told it to not change this. The dollar signs are more or less telling you, don't change that, that's the reference, right? Yeah, here's the minutia. All right, that's still C6 now. The location of this particular 3 is at C6, and it's dividing by 20, right? The location of this 8 is C7, and it's dividing by C10, all right, which is where 20 is located, right? If you wanted to calculate percents, you know that, again, there's probably another function deep buried within Excel, but I did this to illustrate, again, you know, from brute force, all right, that how do you convert a decimal to percent? You just multiply by 100. So I told the initial thing here, all right, you know, equals this particular cell times is the asterisk symbol, 100, right? And it does the calculation for you. If all of these were erased, all right, I wouldn't need to worry, right? You just, once you have it established that this is the calculation, drag this down to here, it does all the work for you, right? Again, it might seem trivial when you only have a few data points, but if in theory you had hundreds upon hundreds of data points, right? You just want to do it work once and then have the machine, the software, do the work for you, right? If you wanted to calculate the degrees, all right, you would go over to either the decimal or in theory a fraction. It doesn't really have it ready. It's everything in Excel is more or less in the style of a decimal. All right, you would take this and multiply by 360, right, and then it would spit this out. All right, once you have your percentages, right, that's really all you need. As a matter of fact, the decimal even, all right, that's all you need to draw a picture like this. So if you wanted the calculator, pardon me, if you wanted Excel, I'll just try to delete this. Cut. If you wanted Excel to basically spare you the task of having to do a pie chart by hand, and that is really one of the benefits of it, is you go up to your options in the menu and tell it where to take data from, right? And then it will give you a slew of different choices. So if you go over to Home here, all right, I have perhaps an older version of this. Insert, here you go. Under the Insert tab, my version is a Mac version of Office. You see over here, there's different type of charts that you can choose from, and one of which is the pie chart, right? So if you choose pie chart, right, and you can get a three-dimensional looking one, which is kind of cool. You can do what is popular nowadays, which is the donut, right? Or you could do the standard pie chart, which I'm just going to go with 2D here, all right? If it doesn't do it automatically, what you have to do is tell it one thing first. Where to take data from, you might just use degrees if you want, or you could use these decimals, right? I'm going to go with the degrees, highlight the degrees, right? And now choose pie chart, and it draws the chart for you based upon, you know, those degrees that you calculated. The software is smart enough to go, well, all right, well, if I added these, it would be 360. So if I cut it up the way that it ought to be, right, that's 54 degrees wide, that's 54 degrees wide, right? This is 72, 36, and 144. It might do it different in the order that you had it, but if you really wanted to, you could move these around, you can change where the wedges are. As a matter of fact, if you really wanted to tinker with it too much, you could change the colors of these, you could spread them apart, you could tip it to a 30-degree angle and make it look more like an actual three-dimensional object. You could fill in labels here, you can change the font of the labels, there's a lot of stuff you could do. So this is another avenue which you could go down to teach a kid who's in middle school, you know, the relevance of the subject of math, right? And give them something to relate to, right? It is our collective inheritance, so that's what I'm trying to encourage you. All right. Anyhow, that's everything. All right. And I hope that I have convinced you that this is the fun part, all right, of math and of statistics in general. I should say of statistics and of math in general. All right. So if you want, I mean, I'll make it available in Canvas in our Pages section in the link. All right. If you want to take this spreadsheet and then tinker with it, you're welcome to. Okay. All right. For homework. All right, please, just to keep pace, all right, do section 12.2 in MyLab. All right, try not to let it linger for too long because it gets increasingly more and more intense, all right? The statistics chapter, especially when we get into normal curves and stuff like that, normal distribution, it's kind of, if you've never seen it before, it might be a little intimidating. It isn't really hard, all right? There's a system to it, but if it's not familiar, you might be a little resistant to it, okay? So start on this as soon as possible, all right? I'll see you on Monday, all right? Be careful out there.